In this video, I'm going to show an example of calculating lattice energy using a Born-Haber cycle. So the question says calculate delta H lattice for MgF2, so magnesium fluoride. And the first question we should make sure we understand is, what is the lattice energy? What does it represent? Okay, the lattice energy is the energy of going from the compound MgF2 and turning it into its ions that formed it. So in other words, Mg2 plus and 2 F minuses. So that's the energy we're looking for, and we are usually given a table of data, a bunch of reactions, a bunch of energies. Some are positive, some are negative, and we're going to try to put them together in a way to make that reaction. And we do it graphically using a Born-Haber cycle. All right, so first let's look at the reactions and identify what they mean. The first one is magnesium solid as a reactant, and that's the natural state of magnesium, the standard state, going to magnesium gas. Now the reason we say gas is because we're simply pulling apart the molecules from the solid and making them separate molecules. So another name for that would be the delta H of sublimation for magnesium, because sublimation is going from a solid to a gas. The second reaction is F2, diatomic fluorine, going to two separate fluorine atoms. And that would simply be starting from the standard state of fluorine and going to separate atoms. That's breaking the bond between the fluorines. So that energy is known as the bond energy. And notice these first two energies are both positive because it takes energy to pull a magnesium out of the solid, and it also takes energy to break a bond in the fluorine. So it's positive energy if it takes energy. The next reaction is the gas phase atoms of magnesium going to an ion, Mg+. So ripping an electron off the magnesium to make it Mg+, taking an electron off is known as the ionization energy. And since this is the first electron taken off the fluorine, we'll call it IE1. The next reaction is taking the second electron off, going from Mg+ to Mg2+. So that would be the second ionization energy, IE2. And those are both positive and quite large. It takes a lot of energy to pull an electron off of an atom. Now the next part is going from a single fluorine atom in the gas phase to a F minus, the fluoride ion, by adding an electron. So that's representing the affinity fluorine has for an electron. So we call that the electron affinity, EA, for fluorine, and we can put a 1 there for the first electron affinity. That's a negative value. It actually gives back energy to do that, becomes more stable. And then the final reaction is from Mg solid again, and F2 diatomic, to making MgF2, the compound. So that's going from the two elements in their standard states to the compound. So that is known as the heat of formation for MgF2. It formed 1 mole of the compound. You know that because it has a coefficient of 1, and it started from elements in its standard states. That is the definition of the heat of formation. That is a negative value because it is always more stable to make the compound. All right, so now how are we going to do this graphically? We're going to first realize that the compound in these examples will always be at the lowest energy. So we're going to go all the way to the bottom and draw a line representing the enthalpy of the compound, MgF2, the compound. All right, and then we're going to try to put other things in there graphically. Whenever we go up on the page, that's a higher energy, and when we go down, that's a lower energy. So the only thing we have so far is that shows MgF2 is this last reaction, which is the heat of formation. Now going from elements to the compound is a negative energy change, so flipping that around, if you go from the compound to the elements, it'll be a positive 1,123 kilojoules. So let's do that by going up from where we started. And this will be not to scale, but not horribly, horribly far off either. So this is magnesium solid and F2 gas. And that energy change is 1,123. So we're going to mark that. All right, then we're going to start doing stuff to the magnesium and the fluorines using the reactions above and try to get to the state where we have these two ions, Mg2 plus and F minuses. Okay, so the next thing we're going to do, I'm going to focus on magnesium. It doesn't matter which one you do first, but let's do magnesium first. We'll turn it into the gas phase. So that's Mg gas, and you note from above that that energy value is 148 kilojoules. That's given over the reaction above. Okay, and then after we do that, we're going to take the fluorine, which is F2, and break it apart using the bond energy. So note when I go from magnesium solid to gas, the fluorine doesn't change. So I could rewrite it, but I don't need to. It doesn't change. But now the fluorine's going to change. So I'm going to write another level, and that's going to be 2F. Going from F2 to 2F, that energy change is 159. Now I'm going to go back to the magnesium, and I'm going to rip an electron off of it. So again, magnesium is still there. We haven't changed it. We've only changed the fluorine. So I'm going to rip rip an electron off magnesium, make Mg plus. That energy was 738. Okay, these are all given above. Then I'm going to pull the second electron off and make it Mg2 plus. That energy is 1,450. So again, this is not to scale, but as long as we have the numbers in, it doesn't matter too much. Okay, now the next thing we're going to do, we're at the top here, and you might wonder why we haven't left more room, because the next thing we're going to do goes down in energy. Okay, we're going from F gas, which is what we have here. This was F gas. Okay, we made 2F gas, to putting an electron on it. That's a negative change. So we're actually just going to extend the magnesium line across and go down to some level which has 2 F minuses. We put electrons on both of the fluorines. We have 2 fluorines here. Okay, notice the energy of putting it on one fluorine is negative 328. So doing it for 2 fluorines would be twice that. 2 times 328. But our arrow goes down because that's going down in energy. And then at that point, we have Mg2 plus. Remember, whenever we don't rewrite it, it stays the same. So it's still Mg2 plus here. We have 2 F minuses, so we now have what we need in products for the lattice energy. And we have MgF2 down at the bottom. So we can extend this line over, and now we know that the lattice energy is going to be this amount here. Okay, that's the lattice energy. So we can simply look at the graph and realize how to calculate that. We have all these values that are going up. We have all the values, everything between MgF2 and Mg2 plus on the left side has got to equal everything on the right side. Okay, so we can say that these things all added up, and I will do that in red here. So I can say 1,123 plus 148 plus 159 plus 738 plus 1,450 has got to equal 2 times 328 plus the thing we want, delta H lattice. So we can then solve for delta H lattice. Which will give you 2,962 kilojoules per mole for delta H lattice. So that is an example of a Born-Haber cycle. And you need to realize a couple things. One is that In this case, we were solving for the lattice energy, but really any of these pieces in this entire cycle could be the thing you're solving for as long as you know all the rest of them. And you can just draw this graph. And the second thing is that these types of problems can also be solved non-graphically by just rearranging the equations you're given, doing a Hess's law type calculation where you flip equations around backwards and multiplying by 2, whatever you need to do the same thing to the delta H, and then if you can get them into a state where you can add them up to get your desired equation, then you can simply add the delta H's you've created. So that's another way you can do it without drawing the cycle.